Welcome to Rockquaculture, a brief look at the world of aquaculture technology at Hillsborough Community College. I am your host, Craig Casper, and for the next few slides and few minutes, we will be taking a look at some of the filtration and aeration systems that we use down on the farm. Traditional aquaculture production in ponds requires large quantities of water. Consider this. Approximately 1 million gallons of water per acre are required to fill a pond, and an equivalent volume is required to compensate for evaporative loss and seepage during the year. Ouch! That is costly. Assuming that an annual pond yield of 5,000 pounds of fish per acre, approximately 100 gallons of water are required per pound of fish production. In many areas of the United States, traditional aquaculture in ponds is not possible because of limited water supplies and the absence of suitable land for production or construction. I'm thinking of Florida here, and that means we have to head indoors. A recirculating aquaculture system, or a RAS unit, maintains aquatic species while filtering and reusing the water. A RAS may be as simple as a single small aquarium or as complex as a multi-unit production system. In any case, the filtration and aeration systems are the most important parts of any working fish husbandry system. So, a couple of basic things. You might walk into the laboratory one day and ask, why is the water so dirty? Well, that's a very good question. Another thing you might notice is that the fish are up at the top and they seem to be piping for air, and you can't figure out why that is either. Or you take a water quality sample and you look in the data, and in the past it was fine, but now all of a sudden, oh my gosh, the nitrogen is off the scale. What's going on? Well, these are all great questions, and they probably stem from the fact that something about your system has failed, either one component or possibly multiple components, and you need all of these things to work together in order to have healthy fish. The other thing that you need to recall is that the RAS components are not only there to hold the fish, but to remove the solids, to remove any nitrogenous waste, which is what we call the mechanical and the biological filter respectively. They're also there to help circulate water, maintain temperature, and provide oxygen and take out any carbon dioxide. So everything has to work together. This is what I kind of call the magic 5 in the middle of our intro to this the last time we were down at the aquaculture lab. So if any of these fail, you've got to do some immediate troubleshooting, especially if it involves a water chemistry issue. And a couple of the mechanisms that we're going to look at involve some of these filters, these different styles that we're going to use, and we're going to see those individually, and that's what we will focus on for the next few minutes. So hopefully you guys remember this slide, or at least you remember us talking about it in the lab. I'm going to go ahead and get rid of that video preview down there so you guys can actually see the rest of the chemical equations and the flow pattern here. But this is the magic 5 that I was talking about, and we've had quiz questions on this. We've had discussions on all the basic parts, and so what I want you to really understand is you are the ultimate person that manipulates the system from the start. Look all the way to the left of the yellow chart. You can see that feed is the first input. So that's the number one place that you're going to have an influence on your biological system, your solids, the amount of aeration, oxygenation that's going to be in the water. And every component here relates to each other. So it's very important that we get all of these things right when we're trying to make healthy fish. So why is all of this important filtration really necessary? Well, if we remember, we have 3 different types that all work together. The mechanical filtration, the biological filtration, as well as any kind of chemical filtration that we might use. And throughout the discussion, we've been looking at mostly nitrification and biological filtration. We've also looked at removing suspended solids and trying to keep the water as clear as possible, basically a bioclarifier, if you want to use that word. About the only way you're going to know if your biological filter is actually working is if you do routine tests on the water, what we've been talking about in water quality in lab. Realize that we're talking about 3 different components of the nitrogen cycle here for sure. We're talking about the total ammonia nitrogen, or what we were calling TAN, and then the ionized and the unionized ammonia. And only one of those is really harmful to fish. The unionized ammonia, or the NH3, that's the one that's usually doing all the damage. So we want to be very aware of what is going on in our water chemistry with respect to those. And the reason that this all is important is because we're really interested in growth at this point. We want our fish to grow as fast as they possibly can to whatever our market size is. And if our nitrogen cycle is not really well maintained because our filtration isn't working, then that's never going to happen. You're going to see a reduction in growth rate, and you could even see fish stress or death. This is what all of that filtration is ultimately getting you. High quality products, in this case shrimp. Imagine being able to raise these things disease-free and to be able to raise them in high densities, being able to have a tank that was somewhat clean. Those things are only possible with really good filtration. And so that's what the Recirc system is all about. One scenario that I often tell you guys about in class is that sometimes you just have to put so many fish into the system, you have to look to find water. It isn't technically true, or in the case of these catfish, it might be true. When we look at fingerling production, the densities are extremely high, and you can see by this picture that the fish literally take up the entire viewing pane. This isn't generally possible in a Recirc system without a really, really robust filtration system, but it is fun to think about. Usually we're looking at about 1/3 of a pound of fish per gallon of water, and that will be optimal for keeping the disease incidence down and keeping the production density high. Much of the material that we consider for export in an aquaculture setting when we're using mechanical filtration is basically uneaten food or some kind of waste products from the fish, what we would consider solids. These are easily removed by most conventional mechanisms. This one in this slide is pretty special though. Some of you have seen this one before. This one's called a Cornell double drain system, and it works by essentially allowing the smaller solids to flow through that small silver pipe there in the left corner. And then the larger solids can actually be flushed out because that black ring at the bottom can be lifted, and all of the larger particulates will be sucked through, kind of like a vacuum cleaner. It's pretty cool to watch one work. This particular unit happens to be down at Aquaculture, and I'm pretty sure that it's down there still in production. Once all these solids are taken from the water, the rest of it is dealing with the solids that are not affected by gravity, what we call suspended solids, or in some cases colloidal solids, and we'll see a couple of ways to get rid of those too. Here's a good example of a rotating screen filter, or a rotating drum filter. As you can see, this one's pretty large. I wouldn't generally recommend this type of a system because of the complexity. A lot of farmers don't use them because they're pretty costly and they're kind of hard to maintain. But as far as being able to remove some of the small particulates from the water, they're pretty cool. One of the things that we can look at for sure is the way that the microscreens interact with the surface of the water. As the drum rotates around, the small particulates get stuck in this small membrane and they're dragged from the water column. Therefore, they stay out of the system and the circulating water continues through. In the next slide, we're going to look at a picture of one of the microscreens up close, and you can see about the quantity of material that they can pull out in a single pass. This is what I'm talking about. Notice here next to this pointing finger, you can see in the right corner some of the small brown sludge that has been captured, and then in the upper left near the captured solids arrows you can see some really good capture. This doesn't seem like much at first, but over time this will clarify the water and can remove quite a bit of the solid material that's floating in the system. Now this is the stuff that doesn't come out by gravity, so this is a real benefit for water clarification. When the unit finally needs to be cleaned, or I would dare say backwashed, the rotating screen becomes so impregnated with dirt that the water level inside the tank where the drum sits actually starts to rise. And eventually that turns on a special float valve that activates this spray bar. You can see the large brass fitting in the pressure regulator on the top of it. And what that does is it blasts the entire microscreen with a great big power washing blast of water. And it rinses all of the dirt into a collection basin where it's exported from the system. And this might happen several times a day on a system that had a lot of suspended solids in it. The only downside to such a system is you have to monitor the water flow pretty carefully, because you can overdrive the system with too much water going through it. You actually strain the dirt right back through the microscreens. We've had that happen before in testing on some systems that weren't properly designed. This slide might be a little bit before its time, but I just wanted to show you guys what usually happens to all of the suspended solids that are taken out of the system. They'll usually end up in some kind of conditioning chamber where you get the start of bacterial activity on the solids and any of the nitrogen material that's in them. These small beads could have been put in any kind of system, and if you recall, if you've gone and looked at some of those videos that Paul Begay illustrated, he talked about these things. These are little bitty polystyrene beads. They're what is in our bead filter out at the lab, and they're what's helping to convert the nitrogenous waste into something that's not harmful to the fish. One of the questions that we need to ask ourselves right away is, what happens if our filter system doesn't really work, or it doesn't work well enough to get all the solids out? What happens? Well, here are 3 points, and below I listed some notes of some words of wisdom from Tom Lasordo. He's one of the people who designed some of the more advanced filtration systems that we use at the lab, and I'm going to let you go ahead and read that one yourself. But the bottom line is, when you look at the increase in the biological oxygen demand caused by the presence of too much sludge or solids, that can be a real problem for your fish in your system, and even your bacteria in your biofilter. You also have water that you can't see through. We talked about turbidity before, and that can be a major issue too, especially if you're trying to view the fish and make sure that they don't have any kind of disease issues. And the last one is that you can actually have gill damage. Some of the fine particulates that get up inside the gill membrane of the fish can be harmful. If you can imagine some kind of coarse sand up there inside a very delicate feather-like organ, then you can kind of get an idea in your head of what the fish might be up against if you have too many solids in the water. As you can see here, the particle size of some of the solids that actually don't come out because of gravity gets to be super tiny. Anything that is settlable, or 100 microns or larger, is going to fall out because of gravity. Anything smaller than that is probably going to stay in the water column until you do something about it. That means either separating it physically by some special filter, or somehow spinning it out of the water column like they do with a swirl separator, or maybe even changing the composition of the water chemically like we would have to do with a colloidal solid. Remember, a colloidal solid is like paint. Things would have to sit for an extremely long time with no disturbance before they would come out of solution, and even then they might not. If something is colloidal on the small end or dissolved, then it's not coming out with physical separation. You have to use chemical separation at that point. So that kind of gives you a rough idea about what we might be dealing with in any aquaculture setting. This is a good example here of looking at different types of filtration devices you might use to remove some of the solids that we've been talking about. This one works a little bit backwards. The slide particulate size is left to right in decreasing size compared to what we saw before, which was right to left. But don't let that throw you. It's pretty clear that something that involved a coarse screen was way different than something that involved foam fractionation, like what Grace uses on her saltwater fish. Anything that's small enough that you have to separate it by a special cartridge with chemicals or something with foam fractionation is teeny, teeny, tiny. You can see here a pretty simple design, something that's called a settling basin. This is one of the easiest, most low-tech ideas when it comes to allowing solids to be removed from your system. The next slide actually shows a picture of what one looks like when it's functioning. Basically, you slow the water down, make it work against gravity, and then fall out of solution. The optimal design would let clear water, or at least fairly clear water, go through the outflow. That helps your filtration units later on down the line. Generally, after you use a settling chamber to get rid of all of the solids that could be pulled out by gravity, you're probably going to have to use some other mechanical filtering device to remove the solids that might be suspended. Anything that we use in our lab or on most of the farms in Florida would fall into one of these two categories of bead filters. In each case, you have small plastic beads that sit inside a giant canister. The design on the right is probably the more common and the least expensive. A bubble wash system uses minimal mechanization to make it work. Essentially, if you stop the flow of water and drain the system, air rushes into the upper chamber and essentially knocks all the beads around and loosens up or removes the dirt. All of that sludge drains to the bottom where you can remove it later. The propeller wash design on the left is used in large industrial applications where you need something that's automated and completely mechanized. They work the same as a bubble wash bead filter, but with the addition of the propeller, a backwash cycle can be set automatically and can really do a wonder when it comes to water clarity. Some of the larger industrial production systems make use of this design. I went ahead and included this slide to show you where the workhorse is in the biological filtration department. All of the plastic beads that we've been talking about, and there are multiple designs, essentially are there for the same purpose, to grow bacteria. So this slide shows you where those bacteria grow. We've looked at this before in some of the other classes, but for a few of you this might be the first time actually looking at one up close. All the engineers really love these types of things because they tell you where the beneficial bacteria grow, how the nutrient cycling works in and out. And as you can see from the outer part of this picture, the nitrifying layer where all of the biofilm exists, that slimy stuff that you guys see sometimes when you're cleaning tanks or you feel it on the side of the pipes or whatever, that's where these bacteria lie. And every square inch of the tank has it after about 4 to 6 weeks. If this layer isn't maintained, then the animals that are using it are going to go ahead and either slow down their production, or they could even suffocate because of fouling. So that's why we have to backwash and clean everything up. This slide here really shows us the optimal formula for a good biofilter. Anywhere around neutral pH and plenty of alkalinity and a lot of good flowing water through the biofilter will help keep the bacteria rejuvenated. If you get the flow rates too high, or you just bombard the system with tons of food that some kind of settling chamber can't remove, then you're going to overwhelm your biofilter and it's probably going to crash. As you can see, this last line, the biofilm regenerates itself often, and so you need to constantly be aware of how to clean it and how to add additional alkalinity like calcium carbonate back to the water to keep your bacteria really healthy and happy. These are some of the variations in media that are out there. This was presented in a conference a long time ago when I was out in Seattle. I think the slide here says 1997. And a couple of really smart guys, Dr. James Ebling and Dr. Timmons, they were trying to discuss the benefits of some of the different types of media shapes. And what they were after was what was the ideal shape media to get the most biological activity. And as you can see here on the right, the best design, ironically enough, is really a coffee straw that's been cut into really small pieces. The problem is that it clogs up almost immediately, and so even a backwash cycle wouldn't clear it out. The one in the middle, that little bean looking thing, that's what's in the middle of our polygeyser, and that has enough channels and surface area in it that it can bring you a fairly high level of nitrification per cubic meter of media, but also that it can actually be cleaned by a good backwash cycle. And that video that I put up on the website that Paul Berg demonstrates how a polygeyser actually backwashes, you can really see that happen. I'm just going to sit back and let you guys take a look at these next few slides. Really various options in design on what you can do. This particular set here is pretty busy. This was a system designed to raise ornamental fish. I believe it was out in California, and it looks like miles of pipe and chaos, but it's really all integrated in a fairly well-designed system, despite what it looks like. This was a great slide to show a summary of how you might put together a chart that could help you know what you are capable of with bead filter sizing. Things like what the volume of the beads might be, the system volume that you're actually trying to handle, and the application where you're going to use it. Maybe you're interested in grow out, which could have a fairly high density, or maybe you're looking at a broodstock system where the density might not be as great, but the fish were very, very valuable. You also look at things like circulation rate of your water, how much air is in the system to provide oxygen to the bacteria in the biofilter, as well as what the dosing might be of sodium bicarb. All of these are considered and can help you figure out what kind of bead filter that you're going to need. And so this little flow chart gives us a real interesting way to look at what we can use as far as sizing criteria for bead filters, and then how much food we're going to throw into the system in order for the bead filter to keep working effectively. So the next thing that we want to take a look at is aeration and also degassing. Basically, aeration is the idea that we're going to add some oxygen to the water and we're going to get rid of the CO2 when we go to degas. Now you guys already remember most likely that the oxygen in ponds and in tanks is less available for fish than it would be for animals that live on land. And we also have to remember that the low DO might actually limit the growth and the bacterial activity within the environment. So we want to be sure that the oxygen levels are as high as they can get and that the CO2 levels are as low as they can get. This is very different in production systems than it might be in natural waters. In natural waters, we're looking at a situation where the diffusion rate of atmospheric oxygen and the photosynthetic production of the little animals and the bacteria and the plants that are all in the water column, they're going to exceed the oxygen use and the oxygen consumption by the fish. But once you move into a confined space with high densities, we find that this isn't the case. And oftentimes, these high density situations, the oxygen use or consumption can exceed that which is provided by the system unless we supplement it in some way. And that's what we're going to take a look at here for the last couple slides. When you look at this basic slide here comparing solubility of oxygen versus carbon dioxide, you can see that while there might be a whole lot of oxygen in the air and very little carbon dioxide in the air, the saturation of each gas in the aqueous environment is very different. Oxygen is somewhat saturable in water, whereas carbon dioxide isn't very saturable at much at all. However, even though we can put some oxygen into water and we can't put a ton of CO2 into water, the reverse is true when trying to get them out. Oxygen doesn't come out of water all that easily, but CO2 is really hard to get out. And so the limitations imposed on the system due to excessive CO2 continuing to build up if we don't degas can be pretty stressful for the fish. And so we want to make sure we take good care of our fish and degas the water any way that we are able to. Now, degassing and adding oxygen to the water. All those mechanisms can be done by industrial scale methods or by things that are very simple and very low tech. What we're going to take a look at here in this slide are a couple of extremely high-tech methods. Now these would be used in production settings when you're seeing, thousands and thousands of pounds of fish. You need tons of oxygen in the water all the time, and sometimes there just isn't a good way to get it in there unless you add it as oxygen per se. And so the mechanism on the right is called a downflow bubble contactor, and what that does is it actually allows you to flow water through that conical shaped tube and add oxygen gas halfway through. That's where that green hose is going into. And you get a little sweet spot in the middle of that where the water's flowing down like a waterfall, but the injected gas keeps rising, and so the water flow eventually pushes the gas down so far where the bubbles kind of roll around at one point in the tube, and that maximizes the amount of saturation of that particular water column with oxygen. It's a pretty interesting way to put O2 into a system, but we generally don't use it in our aquaculture operations because we don't have access to pure oxygen gas. The other thing that you see down there at the bottom are some industrial sized liquid oxygen canisters. Those are those two big white containers on the left, and you can see all of the different diffusing columns there to the right. Those systems are designed in order to really be used as a fail-safe in a lot of operations. For example, if you had a large production system in a hurricane zone, maybe you would be concerned about power outages. And these types of systems can be set up so that they're not actually dependent on electricity for them to function. They actually stay off until the power goes out. And once the power goes out, the valve that is normally being held closed by an electrical current actually opens up and lets the oxygen gas flow out. So you get automatic oxygen going to your fish instead of just a little bit of air. And if we're putting pure oxygen into the system, that brings the O2 level of the water up significantly in a very, very short amount of time. Okay, so we just looked at high technology. Let's look at something that's super simple. We could use any of the devices that you see listed on this list to the left, and they would do just fine for our aquaculture operation down at the farm. And as a matter of fact, we do have air stones, we have surface agitation, we have spray nozzles, we have a sort of packed column, although our column really is used for degassing and not adding oxygen to the water. What we don't have in our greenhouse are paddle wheels, but they do have paddle wheel type devices in some parts of the farm, or they have some other kind of air diffuser that actually allows oxygen saturation to increase in the ponds where they're using it. You can see that air stone there in the middle. Those things are really common. It's just a big piece of very porous like lava rock, like pumice, and you push air through it and it makes a lot of really awesome bubbles. The smaller the bubble, the greater the exchange rate of oxygen into the water. So you always want to have a nice clean air stone, something that's very, very fine in its porosity that can really help you maximize that O2 exchange. The device up there at the upper right, that's just a regenerative blower. I'm going to go ahead and add a slide here in a minute that's going to show you the inside of one of those things. Basically, it looks just like a fan of a jet engine. And as that goes around, it pushes hundreds of cubic feet of air per minute, and that's what we use to power our aeration system too. They're pretty reliable, they generally don't have a lot of problems, and they're not too expensive to buy. And then here's still a few more alternatives to aeration. Now these are items that you might find out in a large pond. On the left is a paddle wheel type design. Those are actually one of the most efficient ways to put oxygen back into your water. And then on the right you can see a large fountain type of an aeration device. Again, another way to kind of mix an artistic statement with something that's completely functional. Both of these work very well, however, they do rely on electricity in order to get the job done. And if you ever have a power outage, these are automatically not working. So that can be a real challenge if you have a highly dense pond or something that's in the middle of a production setting where you need oxygen in your water all the time. So the last thing we want to take a look at is how in the world do we get the carbon dioxide gas out? And these are actually some of the most simple ways that you can do that. Basically, it's called breaking up the water column. The engineers like to call it CO2 stripping, and both are accurate. What you're essentially doing is making the water column that you're pumping out of your system fall down over some kind of piece of plastic or some device that breaks up the water and makes it rain down. Instead of falling in a very tight continuous stream, you spread it out. The more you bash it around, the more carbon dioxide is able to leave the water or to degas. And therefore the water going back into the system should contain significantly less CO2 than what was coming through the packed column when you started. Any way that you can do this, whether it involves high-tech or low-tech, works. I always prefer the low-tech, which is kind of in our budget and is pretty easy to replace if something should break. And all it takes is making the water rain down through a couple of air stones. If you really wanted to do something to add to this and make it a little bit more high-tech, you might be able to actually build such a column where it had an exhaust fan blowing out of the top of the column, kind of like a chimney effect as you rained water through the column. I've seen that done once or twice on some systems to the point that it actually changed the water chemistry quite a bit. Not only did they pull the CO2 out very quickly, but it actually helped this particular lab get around an iron problem that they had in their water. They had high levels of dissolved iron, and so they were using this CO2 stripping column actually to change the pH of the water slightly coming out of the column, and all of the iron fell out of solution. It was a pretty elegant way to solve what could have potentially been a toxic situation for their fish. This has been Rockquaculture. Thank you for tuning in and taking a look at aeration and filtration at Hillsborough Community College.